Oscar. So, good morning. This is about all my Swedish for the moment. My name is Antoine Sirianni. I'm an engineer in microelectronics. I'm coming from Paris, France. And just to start, I wanted to tell you a little joke. So two AIs go to a conference, and the first one asked the second, "Are you here for the conference too?" And the second replies, "No, I'm just here to debug my social skills." Okay. So it's kind of human, you know. So my talk will be twofold. First, I would like to focus on an AI experiment, and then I would like to focus on combinatorics to set up, to analyze the list of standard cells you could put in your library. So I woke up yesterday morning learning that there were a new ChatGPT version. So I had to refresh my presentation. It was obsolete before I gave it. So I have prompted ChatGPT, the new release, to know what he was thinking, sort of, about standard cell library design. So after a short introduction, it defines a number of requirements and objectives. So mainly technology, PDK, target, application target, what optimization are you looking at, and the list of cells. This will be the focus of the second part. Then you go into schematic creation, transistor sizing mainly, and then you go into physical design. So layout, DRC, LVS, and one that is nice is design for manufacturability. And there is also design for robustness, you know, hardened design, which is not possible for AI easily. Then you would characterize the cells, so define the number of parameters and windows you want to go through, and generate the models for to feed up the flow, your design flow. And then you would generate your files for simulation, for layout. And after that, you need to verify and validate. So usually you would validate exercising a design flow, focusing on power or not. So it might be quite complex. You'd need to document and to manage continuous integration. Maybe also some legal aspects that could be important. And then you would consider automating layout, for instance. That was not the case 30 years ago, but I think right now there is a number of solutions to automate the layout, and also some open source ones. And then it says that if you do everything he has mentioned, you are all set and it's okay. Well, it's a pretty good start. So if you look at all those steps, maybe you could add some. If you have some experience in designing libraries, you could add some points. Maybe abutment rules. When you design standard cells, you want them to fit all together when you place them. Another point is the footprint, which is very important for the quality of the routing. Also, there is still, I believe, there is still room for innovation. It's very important to consider education too, which is not really the case as far as standard cell libraries are concerned. Then you would maybe you'd like to contribute to open source. And this one is for Matthew. Maybe you could consider designing a test chip dedicated to standard cells. That would be a nice exercise to maybe to go through. And so this is a wide spectrum, very energetic spectrum, very intense, a lot of details. Where do you start? If you just consider one of the first steps, you want to define the list of cells you are going to put in your library. So how can you broach this question? How many combinatorial cells do you have with 2 inputs, 3 inputs, 4 inputs, whatever? So you can use combinatorics. So you may define a Boolean algebra, a Boolean function, and the symmetric group permutations. Okay, so for n equals 2, you can do everything by n. You have actually 16 functions in the set with a truth table or a table lookup, and you have a number of views representing a function. Okay, as a matter of fact, the way back is not true. You can represent the function using a signature, but the signature doesn't characterize a function because some functions may be 0 or 1 input. You know, there is a kind of a quadratic extension. So there are copies of the sets when you vary the number of inputs. And also, if the function is 2 input, it might be equivalent to another one. You know, there is no reason why you would name a variable A or B. So when you swap A and B, you get the same function. Okay, so how many unique functions do you have actually? So again, you can do it by n because it's quite small, and you get 12 equivalence classes of functions. And mainly, you have 2 inverters, 2 buffers, I call that imp because it's for implication. You know, this function is not usually named, but it's an implication. A implies B. And its negative part, you could interpret it as a binary level comparison, a binary lower down, if you like. It's the contrary of implication. Okay, so you have 12 classes. Okay, and what is it like if you want to solve this problem on the general side? So what we are doing is that we are swapping inputs. So this is a kind of symmetry. This symmetry is achieved by the symmetric group. So what we are doing is that we are applying the symmetric group to the set of functions. So this is called an action, a group action. And one of the nice properties of these group actions is that it partitions the set of functions. And those partitions are the equivalence classes you're looking for. And then there is a very nice result called the Burnside's lemma that gives you the number of classes. So and it uses the number of fixed points. So you apply the permutations to your function, and you're looking at the number of functions that are fixed by every permutation. So this is a nice way to get the number of to get the number of classes. Okay. So if you apply the Bernstein's lemma for n equals 2, you go through this process and you get 12. So it seems to be working. Okay. You can also apply it for n equals 3 or 4. You get those formulas. So for n equals 3, basically you have 256 functions in the set. Actually, you get 80 equivalence classes. So you have only 80 functions to design. Not, or you may have only 80 functions to design, and among them, you have those that are not exactly 3 inputs. So you have to subtract 12, so actually you have 68 3-input functions. And you know about the combinatorial explosion problem. So for n equals 4, you get around 4,000 cells. Okay, so this is a table to sum up those results. Well, the good and bad news is that yesterday morning, ChatGPT was not able to compute for n equals 3. Okay, so when I woke up yesterday morning, I discovered that new release and I tested it. So now it's able to compute all this table. So it fails for n equals 5. So, and if you look at the numbers, to me it's two orders of magnitude. So to me it's huge as a change in capabilities. So it fails for n equals 5. It gives a formula like the Burnside one I showed you, but the numbers are wrong. Okay. So I have packed all that up in a Python package that I've published on how would you say, PyPy or PyPy? Okay. And also it's also published on GitHub. And you can get the orbits, you can get the conjugacy classes, and you can get the Burnside formulas. So from there, what could we? Well, there are many ideas that could stem from this study. So there are other reductions that are possible. For instance, you know that like for instance a NaN cell is a universal cell. So you could design basically a very minimal library with only one cell, a NAND for instance. So this is called a universal cell. So you could do all your designs. It's quasi-Turing complete as far as I know. Then you could reduce using negation, or a more scientific word would be anti-symmetry. Okay. You have also symmetric cells that you can study to reduce the number of cells you might need. For instance, AOI or OAI are symmetric cells. Okay. So another idea would be to study using the same approach. You can study sequential cells, maybe three-state cells, and also multiple outputs. So we could do combinatorics on these various functions to set up a ground basis for library design. Okay, so that could lead to an online open source standard cell encyclopedia. At least for the functional views, all the functions you may need, you could go to an internet website where you have the functions, you have those views on the functional level. maybe also the path, the timing path that are used for characterization. What is possible to do is also to improve the package, because now it's called group action, but it is a bit concrete. It could be abstracted away for any group or any set. Or the user could define the group he wants to use. And okay, and another thing I'd like to experiment is to prompt. Okay, is to prompt or to fine-tune an LLM to see if we can go further. Now it's stuck. N equals 5 gives a wrong result, but maybe tomorrow morning we could. It could be nice to experiment, and I've got the formula using the package, so we could test if by prompting ChatGPT, the new release, we are able to guide it to the solution and maybe to the next step. And again, a test chip would be nice. And all that could be driven by some applications, and I'd like to work on tiny transformers, or maybe a tiny version of a transformer to exercise the libraries, and also to learn how to design a transformer. We need applications, right? Okay, so a number of sources of information, and these numbers, this sequence of integer is well known. So I rediscovered it by the end of June, 2 months ago, and so. I would like to thank the organization to welcome me. It was very, very nice, very easy, very fantastic. And I would like to say hello to my family and friends. Okay. And thank you for your attention.
Thank you very much. Any questions?
Thank you for the talk. Really quite interesting. If we pursue using AI for these kind of open source projects, how do we stop the AI training on the incorrect results that it produces and then publishes on the internet, and therefore degrading the quality of itself?
As far as I know, you have to ask for very specific questions, and if you go into fine-tuning, you need a validation test. Qualified data is mandatory. So how do you qualify data? Maybe if you have a very well-defined criterion with a compiler, and also what you can do is you prepare your data that is qualified, for instance, a truth table, and you get rid of the first token and the last one, because the training will compute those missing ones, and you will try to fill those gaps, and you know what fits in. So this is the main idea of what you could do to fine-tune an LLM, but it takes a lot of it's a quite important. It needs resources, so you need time and people and computers and money to pay the tokens. It's about, as far as I know, it's It's around $5–10 per million tokens. So it gives you an idea of.
Thank you. Some further questions? Well, I have one question then. Transistor stacking, is that something you could take into account? Like how many, especially PMOS transistors, do you have to stack to do these Boolean functions?
When you're speaking of stacking, you're speaking of a 3D or a series.
A series of PMOS transistors typically would be a limiting factor probably.
Yeah, that question is related to transistor sizing, you know. So this project is part of a bigger one.
Yeah.
And but that I haven't published yet. I would with some support maybe. Yeah. And I am able to synthesize a functional description into a transistor netlist, taking into account the number of the size of the stack.
Yeah, I guess it's not just sizing; it's also like noise immunity and how much you can lower the power supply voltage and
of course,
so on. So but it's probably a factor as well if you would like to go low power, for example. That's just
then there is a lot of refinement to do if you go to SOI or sub-threshold behaviors. It's a different characterization. There are a number of timing models that you can use because the classical is you get one timing, but you can get a window, you can get a distribution. So this is really the very first, to me, how I designed that. It's the very first step when you want to go into you want to go down into the hole. Following the white rabbit, you know.
Yeah. Good. Thanks again.
Thank you very much.
All right.